paired with that of bimetals. That means first powder bed we will make it with say 316N, we will build it, then we will drain the powder, we will add inconel 718 powder, from there we will build inconel 718. So one cylinder we are getting in the sense bottom 316, top inconel, bottom 316, top high inconel, bottom inconel 718, top high inconel. It's a single piece like that used to be. This interface property, that joint property, he has compared. He published almost some 30-40 papers. Now he is assistant professor in Sweden, the government, Prasad University. Okay? So he did PhD in NIT Trichy, but he became a professor, assistant professor in Prasad University. Because of this one. Because Sweden has started major European Union project in development of this multi-layers and bimetal structures with this powder bed techniques. So he is part of that one. He is one among the top 10 people there to extend this project to next year. Next. Next. Yeah. Starting from basic optical microstructures, like anyone else, we used to work with. So we used to have optical microstructure. Optical microstructure space, the basic microstructure, as I said that below few microns, 2 microns, 3 microns resolution we cannot see. Up to that whatever finer details we are able to see, such as porosity, some interfaces, grain boundaries, such kind of things only we can see. That's what we need at the first stage to understand. First visual inspection. First of all, we should give you our make name. Whether the component outcome is good or that is the primary thing. Once you are satisfied with your eye that the component appears to be good, we will go to optical microstructures. There we will see that fundamentally finer porosity and other things are boundary distribution and other things quite good. Then we will go to phase analysis. XRD. Normally this is the process normally we can adapt. XRD. XRD will give us phases. It has melted down and solidified. During the solidification process, what kind of phases that it has found. Please understand, XRD is not chemical analysis tool. XRD is not chemical analysis tool. XRD is phase analysis. I'll give you a small example. I have taken aluminum alloy with silicon carbide reinforcement. Mechanically, many people will use composite, matrix composite. Aluminum matrix, silicon carbide particles reinforcement. If I do chemical composition, it will do aluminum this much, silicon this much, carbon this much. Okay. But whether aluminum silicon carbide together it is available, aluminum carbide is there, or silicon carbide is there, aluminum silicide is there, we don't know. Chemical analysis will give chemical species quantification and analysis. XRD, any diffraction will give us phase based on crystallographic origin. That means the way the atoms are arranged patternly in a periodic way. So this information will give, if I am doing on the same material, aluminum, silicon carbide reinforced system, I will identify aluminum peaks and rate. That means aluminum may have some silicon inside and matrix. Whatever it may be, aluminum related peaks will get. Plus silicon carbide separate peaks will get. By seeing that peaks, I can confirm that whatever particles inside are there, silicon carbide particles. Maybe titanium diboride diameter or zirconium carbide diameter. Whatever I am keeping as a reinforcement, exactly you can identify. That is called phase analysis. All diffraction techniques. X-ray diffraction, electron diffraction, synchrotron diffraction, nano diffraction, electron backscatter diffraction, any diffraction. The moment you hear the diffraction name, there is a phase analysis. Okay? This phase, cementide is there, Fe3C is the phase, not Fe this much carbon is there. Okay? So it cannot give individual element, how much carbon is there, how much iron is there, it cannot give. It can tell you that this is the iron carbide, and this much iron carbide is there, that also it can tell. That is the difference between XRD and chemical compound. Many people, because when I was in charge, I used to say, sir, I want to see what are all ingredients. The terminology I used to hear very funny. Sir, I want to see the ingredients of this one. By hearing that, I used to say that what kind of ingredients I am expecting. So he used to say that, sir, it is aluminum alloy, it is not this, this is that. So I want to see the what all elements are there. He used to come to XRD. XRD cannot be the element analysis. Go to spectroscopy or sample the dance or whatever. Some people will say that, sir, I want to see what all phases. You come to spectroscopy. Spectroscopy can give you only individual elements. It cannot give you phases. So vice versa. So you should know what kind of phase, what is your requirement. Based on that, you have to pick your characterization. So my emphasis on this entire lecture is plenty of characterization tools are plenty. What are the basic tools? What kind of information we can get it? What way that is useful? Normally, especially in additive manufacturing, what are their potentialities? That's what I'm trying to emphasize. Additive manufacturing wise, only one thing that we can have it. In situ techniques became very popular. The same XRD, in situ XRD became popular. Optical systems, in situ optical systems. Okay. This is typical X-ray diffraction analysis. It is nothing but plot between intensity versus Bragg angle, we will call it as diffraction angle. Let's not much worry about this one. We are not dealing with fundamentals of what it is. If you are able to see this kind of plot, this you have to mark it. Without marking this, it's of no use. Because every one peak corresponds to one plane. A set of 5-6 planes will give you what phase it is. That information will be. That information is mostly enough for conventional XRD as a user, not as an XRD expert. As a user, yes, we can get it. But from XRD, what all information we can get? From XRD, we can get complete crystallographic information. On XRD data, if you apply the field analysis on statistical analysis method like this, you can see atomic positions in the unit cell. Okay, probably in material science you might have studied cubic system, 8 corner atoms. Normally I will show the room, all 8 corners has 8 atoms. Center one hanging ball, BCC. Every wall center, FCC. So this is how the atoms are arranged for that system. How to know that one? I cannot go inside that one and see whether wall is wall center is atom is there or wall center atom is there. But through this I can get it. This will give you direct correlation. One simple XRD scan can confirm you whether it is BCC, FCC, HCP or whatever it is. Whether it is single phase or multi phase. What are those phases? What are their quantities? What are their crystallite size, grain size? What is the strain inside the lattice? Beyond that, if you go, what is the dislocation density? What is stacking point energy? What is atomic position? What is lattice disorientation? You can list something like some 30-40 applications from one XRD scan. From one XRD scan, you can do, in fact, by doing one XRD in 2012 or 13, I have done one paper from one XRD. It was published in Physical. It is to study how precisely we can calculate the crystallite size, the grain size, using this one and correlating with other things, with statistical approach. So this is one small paper we have written. One paper is published in Physical, one paper published in Material Scan. How that we can explore it, nothing else. Okay, so selective laser melting we have done on 316L, that is austenitic stainless steel. L stands for low carbon. Okay, to avoid sensitization, carbon will be reduced with some additional aligned elements so that making more stable, more corrosion resistant, more tough, more efficient in application. Such a kind of material, if you analyze this is electron backscatter diffraction outcome. Electron backscatter diffraction is an attachment to SEM. Not all SEMs can have this one. it's an attachment. But if you have EBSD, not EDS, so many terminologies will be there like this. EDS, chemical composition. EBSD, electron backscatter diffraction. I said diffraction means what it is. Phase analysis, complete crystallographic information. It will give you this kind of structures also. It appears to be like microstructure, but it's not really microstructure. Okay, it is the orientation imaging map we will call it. OIM, orientation imaging map, or inverse correlation map, Kaplan disorientation map, all are maps. Some terminologies people used to use as a micrograph also, something like that. But conservative, these are all maps because every location, based on the diffraction, based on the lattice orientation, it will give color. That's it. Okay. So at the grain boundary, what is the orientation? Adjacent to that, what is the grain boundary? Orientation difference is there, color difference is there. Based on that, it is there. Each color will have one orientation. That means my unit cell, Rubik cube, is standing like this. If it is tilted like this, one color. If it is tilted like this, another color. If it is rotated like this, another color. Like that. Based on the small angular difference also, color variation. So you can understand. This is the typical microstructural features in the form of map evolution. The bottom images also appears to be like the top one, as if like it is reduced from it. As it is reduced, the bottom one is grain boundary map. That means the lines are grain boundaries. But in the terms of colors are there. Each color indicates misorientation. That means this is the boundary. This side